Okay, so welcome everyone. It's a pleasure to start this event on the AI reasoning and mathematics, organized jointly with the Bernoulli Center for Fundamental Studies. AI has got impressive developments over the past years. It works particularly well in many applications where the data is abundant and where the next token is fairly well performed, as in this example. We also know that there are some logic capabilities and reasoning capabilities of current models. If A implies B, B implies C, A implies C is correct. It's understood. We don't know how far this can go. We'd like to use AI to maybe help assist mathematicians as well. But of course, if you ask such a question, the answer may be correct, not necessarily by reasoning, but by just memorizing the thousands of documents that discuss such a Das Fermat result. And we know that memorization can be strongly misleading. That's one of my favorite examples in this camp. Every year, everybody almost who teaches probability, at least a very large percentage of people who teach probability, talk about the Monty Hall problem. I teach it in this very room every year to the second-year computer science students. And this is a classic. Who has never seen it? You have these three doors. One is hiding a gift, the car. Two are hiding goats. You pick one, and you hope to get the car. Usually, the host doesn't tell you what happens. In this case, I told that I did find the car already with my first door selection. But now I'm still offered to switch door. The paradox is that it's beneficial to switch door, which is surprising a bit the first time you see it. But of course, here it's so close to the true Monty Hall that the memorization kicks in and says you should still switch, although you got the car. So this is, of course, there are many examples like that. This doesn't take down the power of many of these models that are really remarkable, but it does say that reasoning and memorization are not the same, and we'd like to understand the limits. We're lucky to have three outstanding leaders in this area, Sami Bengio, Christian Szegedy, Teng Luang, for 3 talks. And then we will also present a recent collaboration with Apple and MDS at EPFL, and the new initiatives on AI for math in the last half hour. So without further ado, I will introduce the first speaker. Sami Bengio is a senior director of machine learning research at Apple. He got his PhD in computer science at the University of Montreal. And then spent quite a bit of time here in Switzerland at IDIAP in Wallis. For some reason, we let him go out of Switzerland, and he went to Google, where he was a distinguished scientist for several years, heading in part the Google Brain team. He's on the board of NeurIPS and been chairing many important conferences in this area. It's a great pleasure to welcome you, Sami, for the first talk. Yes, I'm going to pass you. Tu veux que je te le mette?
Is it working?
Seems like.
All
Let's
right.
check. The slides move.
This is the move?
Yeah.
Okay.
Okay.
Ooh, and then
Il est
back.
un petit peu rusty, sinon, t'as toujours...
All right. Thanks, Emmanuel, for the invitation. And thanks, everyone, for coming. So I'm going to talk about reasoning, and in particular, one problem called the length generalization. And we'll see that in some cases, it might be easy. In other cases, it might not. I'm going to talk about some what we have learned in the past year about all that. We heard about reasoning. Let me tell you a few things about reasoning as a start. What is reasoning? Well, there's no very good definition in the field, but for us, it's usually when you need to take a decision as efficiently as possible by composing simple already learned or simple concept that you can learn. And it's the act of decomposing a hard problem into smaller ones that you can solve that is what I usually call reasoning. As an example of this, suppose you have this problem on the left where you're seeing a pair of symbols and you have to say whether they're the same or not. sounds like easy. So on the left, this is the training set you would get. And you can see that the red triangle, it's a good one, and the two blue circles are a good one as well, and the other ones are not. But in the test set, when you're going to be confronted to new examples, you might see combinations that you've never seen in the past. For instance, two symbols that you've never seen together, or even symbols that you've never seen before, but you just know they are not the same, or maybe a problem that is expressed with more symbols as input, but you still have to say whether they're all the same or not. So these are all kinds of generalization that you may want to expect, but it's going to be hard, and that's an example of what reasoning is. So for us, reasoning comes with two kinds of features. One is the idea of being able to extrapolate. So because these combinatorial problems, you will never see enough in your training set, so you will always be in a setting where it's out of distribution. And so you need to be able to compensate for that by recombining simple methods that can be, once recombined, able to solve the unknown problem. And the other one is efficiency, because if you are not recombining properly the things, then you actually would need a combinatorial number of training examples and time to train these models. So that might work for very big models and look like it's working, but it might only be memorization. So one example I'm going to focus on more particularly is the length generalization, and in particular, some of those that are hard. Here, the parity problem. So what is the parity problem? You're given training examples of the kind here where you have squares and triangles, and you just have to say whether there's an even number of triangles. Seems simple. And if your data is only composed of examples of the same length or less, it's going to be easy. You can train that easily. If in the test set you're given to be given longer sequences, then suddenly most models failed. So that's what is this working? Well, that's what we see here in a paper from Google from a few years ago, where they train up to large models. And here is the region that was used for training the models. And so when you test the task in the region where it was trained for, it's working perfectly. The accuracy is 100%. But as soon as you get longer examples, so the sequence of test time is longer than the sequence at train time, then it degrades very quickly. There are many ways to present the problem, and for most of them, it's failing anyway, so I'm not going to go into details of that, but you can see that it's actually failing even for very large models. OK, so now let's go for I'm going to present two work. This is the first one, generalization of the unseen, and this is a summary of a work we did at last ICML. This is with Emmanuel and Ario, who are in the room, and also with Kevin, who's a PhD student of Emmanuel, I believe. So let's talk about another problem, a simple problem, the majority problem, where for this case, you have 3 voters, and they can vote +1 or -1. That's the whole training set you will ever be having, because that's all the possibilities. That's easy. That said, at training time, you are only going to be given a subset of that. And in particular, it's going to be a structured subset if you want. You will never see x1 and x2 voting -1 together. So you will never see these two examples. They are kept secret. The only thing you see is the training set. So now when you are going to try to train a model on these 8 examples, of course you see it with only 8 examples here, but think of it in a larger dimensional space where it's more interesting. There will be many functions that can be compatible with the training set, and yet only one of them will be compatible or correct on the test set. So actually the family of functions that will be, oh, sorry. Why is this? Here. Yes. So the family of functions that, maybe this is here. No. The family of functions that will be compatible is the right function, the majority, plus this delta x times 1 minus x1 times 1 minus x2. And the reason is that this part, 1 minus x1 times 1 minus x2, is always going to be 0 in the training set, because either one of these two will be always equal to 1, because they're never minus 1 together. That's what we said. So one of these two terms will be equal to 0. And so you can put anything you want in this delta x function, any function of your choice, and that will be compatible with the training set. So there's a lot of functions that can be compatible with the training set, but only one of them is the actual one you wanted to get. And the question is, when you train a model with SGD, which one are you going to get? To study these things, we developed this concept of generalization on the NSYN. And we went to the extreme, and we are thinking about the setting where you are given all the examples of the domain for only part of the domain. And that's the omega dash minus u. And you can train the model with all the examples in that dark yellow. And then at test time, you're going to be tested on examples on the light yellow, which you've never seen. That's the unseen. So we'd like to try to measure how good you are going to be on this part of the domain that you've never seen, even if you have access to all the training set, all the training examples that can ever exist on the part that you can see. Is there any hope in that setting? And we think, by default, it's not going to be good, but there's some hope, and we're going to talk about that. So for the purpose of the paper, we only studied a very constrained setting. We're only looking at Boolean functions. We think it's enough to think about combinatorial and discrete examples, which are usually a staple of these reasoning problems. And as we know, these Boolean functions can all be represented as a sum of monomials. In particular, so the majority function that we talked about at the beginning is just these 4 terms, x1 plus x2 plus x3 minus the product of the 3 divided by 2. That's the solution. That's good. So when we look now, as what I said was, in our setting, there's a part that is going to be the unseen that you can describe. Here, I say, well, in the training set, I will never see the first variable x1 equal to minus 1. That, when you define this unseen, you know that there's a family of functions that will be compatible with your training set. And in that case, it's similar to before, f of x plus delta x times 1 minus x1, because 1 minus x1 will always be equal to 0 for this training set you have. So it's arbitrary, the function you can get, or to be precise, the delta x you can put. One more thing to talk about. The degree of a function is just going to be the maximum degree of your sum of monomials. And the degree profile of a function is going to be this vector of the number of degrees you have, where each term in that vector is just the square sum of the coefficients of all the terms that have this degree. So to give you an example that I have here, the degree profile of x2 plus half x2 plus x3 is this vector, because the first term is all the terms of degree 3 plus all the sum square of all the terms in degree 2, then all the terms of degree 1 and of degree 0. And you can then compute this vector and compare it between two solutions. So if you remember, so here I give an example of a degree in the case of the unseen. So if you have the function f of x equal the product of x1 and x2 plus half x2, x3, and x1 is always equal to 1 at training time, then actually there are two functions that are compatible with this. And they both have the same degree, degree 2, but they don't have the same degree profile. The first one has this degree profile, this vector on the left. The second one have this vector on the right. And so they are different. And we're going to focus on the terms that have the highest degrees in that vector. So what we are going to be able to say with all that is that for some very simple class of functions, first for random feature models, and also then for diagonal linear neural networks, these very simple models that you usually never use for real, but are useful for proving stuff, you can show that when there are multiple solutions that are compatible with the training set, the one that will be chosen is the one that has a minimum degree profile among all the solutions. So now we have a good idea of when there are multiple solutions, which one the model will choose if you train them by HGD. While we prove that for these two class of functions, we also did experiment on a much larger set of functions. And in particular, what we observed is that for transformers, which are the class of functions that most people use these days, you also experience the same bias towards this mean degree profile. So what does it mean? Let me give you, again, a simple example. Suppose you have a function of 15 variables, but only the first two are interesting. So the function is just the product of the first two. The other ones are never used. And you never see the first two as being -1 together. So in that setting, there will be multiple solutions. And what we observe for the random feature function, so the graph on the left, is that what you are going to find, so each color here is one of the term. So there's a term in the constant term, there's a term in x0, a term in x1, and a term in the product. If we wanted, the correct solution would be the term in x0, x1, so the orange one. That would be the solution we want. But instead, we're going to get the term in x0 and the term in x1 to be both high, and the term in 1 to be -1. So we're going to basically get the solution we don't want, but that's the one that has a minimum degree profile. So it converges to that solution. We see the same thing for transformer, about the same behavior. It doesn't work as well for other classes of models, so there seems to be some leakage for MLPs and mean field. That means that the correct solution is also there. It's a combination of the minimum degree profile and another solution which has a higher degree profile. Let me go now back to the problem we stated originally, the length generalization for parity, to study this in that line. So for -1s and 1s as an input, the parity problem is the solution that you're looking for is just the product of the variables. It's as easy as that. There are many ways to express it. The way we are going to look at it is by considering all problems that have at most a given number of -1s. And so we can train models with at most, say, 10 -1s and see what happens when we show 12 -1s in the problem. And that's how we're going to try to see the length generalization problem in that length. So it turns out that you can actually see, that if you're only given a bounded number of -1, R here, for a problem that has, say, k up to k variables, then the mean degree profile will actually be R. And so you are going to have an error that will be quite high as the difference between R and K grows. And that's indeed what we observe when we do the experiment. This graph shows the coefficients of the monomials, of the degrees of the monomials of the solution that is given. For the problem of 15 input variables, what you'd like is that there's only one for the one term, which is the product of all the 15 variables, and that's the black point on the right. But we actually obtain much smaller, a combination of other terms that depend on how many inputs we had for training, unfortunately. So that corresponds to what we were expecting. That explains why it's actually hard to train to solve that problem, no matter how big your models will be. So this was the first part where we tried to get an understanding of why these problems are hard. We gave an example of the length generalization problem and tried to show that, unfortunately, there is a bias in how we train our models that will go to the mean degree profile solution when it exists. And if it's not the solution you want, it's not going to work unless you add some biases to your model, some regularizer that pushes the model towards where you want to be. And this is an open problem. I'm going to switch to the second part. Check for time. What time?
Started 5 minutes late, so probably another 20 minutes.
Perfect.
I'll make you a slide.
Yeah, should be fine, and there will be time for questions. So I'm going to talk about the second paper that will be presented in next week at ICLR in Vienna, and that's joint work with several people from Apple, Hati, Arwen, Itai, Noam, Omid, who's in the room, Josh, who's in the room, and Pritam. And the starting point was basically to try to understand, okay, what are the class of functions that transformer will be able to learn with respect to length generalization? We know that at least parity is going to be hard, but are there other problems that are hard? Are they all hard? Or is there like a distinction between it? Can I predict if one problem would be hard or easy to solve? And that's this analysis. So let's start again by saying, okay, if we're interested in solving algorithmic tasks like addition or sorting or parity, again, suppose you're given a training set of a given length and you want to solve it for problems of larger length. We know it's going to be actually hard for many problems. So there's a lot of people have worked on that, and we talked about it in the last few minutes. I already showed you this graph on the left about the parity being hard, but it's not just about parity. Here on the right, I give another example of a hard problem. It's the variable assignment problem. And so there's a long list of such problems where you train on some length, and it's hard on longer length. So we know that. And we wanted to understand, okay, where do we go? Which ones are hard and why? So we start by taking a simple one. It's the counting task. For the counting task, you're given two integers, a and b, and your task is just to output all the integers between a and b. So a plus 1, a plus 2, blah, 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 b. So these are examples on the left. And I think you get the point. The question is, if you train on examples where the difference between A and B is up to some distance, here 60, what happens when you try it on longer distances, up to 100? It works. Actually, it is an easy task. So this is a length generalization problem that is actually easy to learn with a transformer, contrary to the parity problem. So what's the difference? Well, let's try to understand, okay, how come a transformer is even able to solve this task? So if you think about what a transformer is, and think of it as a black box for now, it is given a context, the gray part, the x here, and it has to output one value, the next one in the sequence. And that should be true for any context and any size of context, up to the actual size you have, of course. So the same function will be applied no matter how big the context is in the limit of what your model was trained for, of course. As you know, if you were to do that with Python instead of a transformer, there's a simple algorithm that would solve this task. You can write it in 5 lines of code. And that algorithm doesn't even look at the length. I mean, it's there if you wish. It's in x. The x variable is a list of a variable size. And no matter how big it is, you can just apply the same code. It's going to work. There's no distinction whether it's bigger or smaller than a given length. It's the same code. So if we were able to make sure that the transformer, when you train it, actually learns that function, then we know it's going to work for any length, because that function is not specific for any length. And we also know, for various reasons, that, and I'll talk about it, that actually transformer can represent that function. We know it can. The question is, will it? But we know it can. So what we think is that if the problem you want to solve can be represented by a transformer, and it's easy to learn it, then it is going to learn it. It's going to be the function that it learns, and it will learn. It would work on any length. Now, what do we mean by simple to represent? So what kind of family of functions we are going to be able to learn with these transformers? Turns out that some people before us thought about a language. They call it the RASP programming language. And a RASP programming language is a language where each layer of your transformer implements a function in that programming language. And there's a set of functions that are compatible, a set of functions that were built for that, like KQV is actually the attention mechanism. And there are other such functions, but they're all very simple functions. If you only use the combination of these functions, then the transformer will be able is able to learn it, because it's only a combination of these simple functions that you put one after the other. The input of one is the output of the other one, and it's going to work. For the purpose of that paper that we wrote, we actually simplified it because RASP was actually a set of too many functions. Some of them were actually hard to learn. When we keep only a subset of it, and we give examples, for instance, there's no loop. It has to be only functions of the whole input that it sees. And so we get a subset of RASP. We call it RASP-L. And with this, we think that the algorithms that are going to be able to be represented by RASP-L, for which you can actually learn, you can write a RASP-L program, these ones will be learned by a transformer. And so we can predict beforehand whether it will generalize to longer length. So that's the conjecture that we haven't proved, but we have tried empirically. And so this is some of the experiments that we have done. There's many more in the paper. We came up with a long list of tasks that are of the type length generalization. So you can train on smaller length and test on bigger length. And we tried to write a RASP-L program for each of them. And so the table on the column on the left are the tasks for which we were able to come up with a RASP-L solution. And the column on the right is those for which there was no RASP-L solution. And in particular, there's the parity here, indeed, that we know there's no good solution to it. So then we actually trained transformers on each of these tasks separately for a given length, up to 40. Then we tested a bigger length, 50. And then we asked ourselves, OK, which ones are going to work? And we get the answer that we wanted. Otherwise, I wouldn't talk about it. But basically, all the tasks for which there was a RASP-L implementation of the task, the transformer was able to learn it in a way that was generalizing to longer length. And all the other ones, it wasn't. And it was basically providing a chance for each of them. So that's the summary of the second part. Transformers can learn some of the hard tasks, but they have to be in some family, those that, for what we think at least, can be implemented with a simple programming language. And at least now we understand why some length generalization problems are hard and others are easier. And I think with that, I am done. And we have plenty of time for questions, I think.
Yes, thank you, Sami. There's a microphone because it's recording. So I'll pass the microphone.
Thanks for the talk. I was wondering, are we humans good at length generalization, right? So if we learn addition, we're not going to learn, 3 by 3 and then generalize to 7 by 7, right? So we're taught the algorithm.
Yeah. So the equivalent of the RASP-L program, which is
but
the
we're
algorithm.
taught like step by step. So can you comment about this way of learning?
And you're asking me...
No, but I'm asking you, so maybe is the strategy correct to try just to learn from examples, or should we as humans teach the machine, you know, to learn directly, step by step, the algorithm?
I mean, this is a meta question because everything we do in machine learning starts from examples. And you are basically saying, oh, maybe it's the wrong strategy. We should start by teaching algorithms in some other ways than by examples. And maybe that would work.
Literature on step by step where you try to guide the machine to...
What we know, and we have in the first paper we talk about it, but I didn't talk about it now, it's what we call curriculum learning. So many people before us, but we also have worked on curriculum learning, showing that indeed, if you decompose a problem into an easier part first, and we did that for, say, for the parity problem, for instance, you can learn problems of size k with small k, and then the same model can then be used to update the model with size k plus 1 and plus 2, and etc. And actually, it helps moving the mean degree profile up to much nearer the right solution. So that's one of these biases that I was talking about. There's no hope if you don't put a bias. So one bias is the curriculum learning, starting from small and helping the model grow the solution where it should be. But that's a big prior. We needed to know how to do it. In that case, that's the solution. What is a more general solution to this problem is a harder question.
Thank you for the interesting talk. I was just wondering, so for the Raspberry programs that you showed, I guess they are relatively simple programs to write in Raspberry. So I was wondering, what happens if you take, for example, a random Raspberry program, which is quite a bit more complicated? Is it still easy to learn and generalize for transformers, or?
I suppose. I think we tried many, not the ones I showed, but in the paper there's a long list of those that we tried, but are they all simple? I mean, it's up to you to check. But yeah, they can be more than just a few lines or just a few number of layers in a way. Yes, that shouldn't change. Yeah.
Do you prove it, or do you just give up after a while? Like, how do you justify this?
It's a good question. I don't.
Like, is it because you?
No, I think it's more the latter. Yeah, we did not prove it. Yes, we search hard. Humans search hard, not proven. As I said, it was just a conjecture.
Adding to that
Yes.
question, so this Rasp language, it's not complete, so there are
Yes.
algorithms which are not representable.
Absolutely, yes. Yeah, it's very constrained.
Sorry, does it mean that transformers also constrained?
No. Well, so again, there are two things here. The first question is, so the transformer will learn. Will it learn a function that actually generalizes to any length? It's not the same question as will it learn. It can learn. I mean, it has the property. Yeah, it has the property to learn almost any function that is reasonable. So that's not the problem. Will it generalize to with the bias that you have in mind? That's the question we had.
So yeah, is it possible to kind of train on different tasks, but to kind of just learn the idea of generalizing to other lengths? You know, I don't know if that made the question clear.
Yeah, I think.
The idea of generalizing.
Yes, I think there's. I think it's the right thing to do, but it's not so simple. The domain will be different for each of your functions. But again, the problem is, as we said, we don't have a. We know that all these problems will suffer from the mean degree profile, unless you put some bias, like a curriculum learning approach. And these curriculum learning approaches are unlikely to be the same for every length generalization problem. Maybe they are. Maybe they are. In that case, that would work.
Maybe another related question here. So if we take some of the maybe open models that have been pre-trained, So what happens with the experimental results on these kinds of tasks?
Yeah, I think it's the same. Arjo, you worked on that. Oh, sorry, you're talking about which part?
Well, so my question is, when you showed experimental evaluation on transformers, these were, I guess, transformers that that start from random weights or something like that, right? You only train them on the
task at yes,
task,
yes.
Right? And so what happens if you?
Well, so for the parity problem, we tried also fine-tuning big models. That doesn't change. Actually, some of the results from Google were on fine-tuning models.
Okay.
Same.
So with
same problem.
The same limitations appear experimentally.
Yes. So as you add tricks, so fine-tuning plus scratchpad plus other techniques that they show at some point, it's getting better. So you can solve longer and longer, but it fails about at twice of the length. So it fails at some point. So it's more, it's not really solving the task.
So thank you for the nice talk. For the first part of your talk, if I understood correctly, when you were talking that the transformers have a mean degree bias, you were explicitly emphasizing that this is true for stochastic gradient descent. If you use other optimizations like adaptive optimization, ADAM or ADAGRAD, what happens?
I think it's the same for ADAM.
It's the same.
Arjo confirms.
Okay, so it doesn't, it's independent.
But I mean, all of these are gradient-based approaches. Right. I don't know if you were to use another kind of optimization problem that is not gradient-based.
Okay, okay.
Yeah, it has to be kind of local in some way.
It has to be low, yeah.
If you think about, say, genetic algorithms, I don't think we can say anything about these approaches because they are population-based. It's a different setting.
Okay, okay, thank you.
Thanks for the talk, and I just would like to follow the question regarding the models. Do you have any specific requirements regarding the model or the transformer you're using? Because you mentioned that you do all the techniques like fine-tuning, this kind of thing, right?
Yeah.
And in terms of size of the models you're using,
no,
this kind of thing.
We tried many sizes, and like in the starting point where I show experiments from others, they went up to 64 billions of parameters, but also tried a few million parameter models. So, I mean, it's better when it's bigger, but it doesn't really solve it.
There is always a limit in this
Yes,
sense.
there's always a limit. You're right.
Okay, thank you.
It's my compute. But I don't think, I don't think you're never solving the problem just by making it bigger. There will always be a bigger problem that you can go with that will also be bigger than the bigger model that you're trying, because it's combinatorial.
That means we are reaching a kind of barrier, and we should change our thinking.
No, what we're saying is if you just try training bigger models, that's indeed, you're limited. Yeah. But you can think of other ways. You can add regularizer. You can change some architecture. You can change how you train, or how you show the examples. There's many things you could do, but just growing the size of the model will not do it.
I see. Okay, thank you.
There's one there. Oh, there's two.
Okay. Hello. Thank you very much for a nice talk. So, question about the first part, learning, then parity. So, I guess the question is, in many of these learning algorithms seems to have the side property that they're robust to noise, like small noise on examples. But their parity is like a crypto primitive.
Yeah. Yes.
So if you would be able to learn parity, would you like give up that nice property? That you're like tolerable to noise tolerant?
It's true that, I mean, in combinatorial problems in general, each or discrete problems, each symbol is important, and that's the nature of combinatorial. There might be problems that are in between where it's combinatorial, but it allows from local noise in a way. I don't know if there is a generalization of the parity problem that looks like that. Do you have an idea of that?
Sensitivity makes it hard, and so in Boolean function it's high degree it's hard. But then we also know examples where you can be noise sensitive, but you have a hierarchical structure, like those staircase function, that still helps you to learn because the model can progressively. But if you are like, if you're highly noise sensitive, it's not good.
So these discrete problems are really, you are not robust to noise by design, but there might be a class of problem in between. It's still going to be hard, but maybe easier because of that.
Right next to Ola. Next question. So what the standard approach is trying to do is to basically compile the algorithm into the weights of the transformer, right?
So that's the Raspberry thing you're talking about.
Right, exactly.
Yes.
But I'm wondering whether the solution, more promising solution might be to actually learn the program.
Oh no, sorry, I didn't understand. We are not doing that. We are learning. No, what we said was if the program that we're looking for is easy according to what we say, it is going to be learned. We're not compiling it at all. We learn it by example.
That was a metaphor. I meant like you represent the program via the parameters of the neural network. But I was wondering if you could actually learn the source code of the algorithm itself. So because that would then by definition generalize, right? So kind of find a low Kolmogorov complexity solution where you make the source code explicit.
I mean, there's a lot of work today in learning to code. They use a very different approach. It's they learn multiple coding. They learn by being shown code, and it's certainly a valid approach. It should be pursued.
But I mean, the code could remain latent, right? You could still just be shown the input-output examples, and you're trying to infer the code that would generate the outputs from the
actually we had it's similar to our Bullformer paper. So we have an archive paper that does exactly that. You're showing pairs of examples, input output, and the output should be the formula that is compatible with that. And it works. I mean, there are limitations about just the size of the context. It needs to contain all the training pairs that you want. And so it can only solve small problems because of the context size. It's limited by that. But despite that, we got pretty good results. Even if you are not showing all pairs of examples, if you are shown enough of them, it's going to find the formula that is the most likely to be compatible with all the training examples. So yeah, that's a valid approach as well.
So in the second part of the talk, you showed that the set of problems on which you are able to generalize is limited by the representation strength of transformer. So did you think about modifications to the architecture that could increase this set of examples or problems?
No, but it's a good idea.
Right. Good. So thank you very much, Sami.
Sorry. Stuff. Who's next? Christian. Oh, forgot about him. Christian. Cool. All right. Hello, hello. Hello?
Works?
No. Yes?
No.
No? Okay, it works now? Yeah, okay. It's mostly to record. Our next talk is going to be given by Christian Szegedy from XAI. So Christian has a PhD in math from the University of Bonn. He worked first in a chip design company, actually, at Cadence. And then in 2010, he joined Google, where we were colleagues for many years. And he worked on many problems related to deep learning and computer vision. I'm sure you've heard of adversarial examples where he worked a lot for computer vision. He worked on the inception network in computer vision. And he also worked on the batch normalization algorithm. You've heard of all these pretty famous algorithms. And in the past 7 years or so, he mostly focused on AI for math, auto-formalization, and the development of memorization and hierarchical transformer networks. Last year, he left Google and co-founded xAI. And today, he's going to tell us more about automatic formalizations of mathematics.
Thanks a lot, Sami. So yeah, I mean, it's not very surprising that I'm talking about this because I have talked about this for like 8 years now. So that's my pitch. It's still not done, but so basically it will be a very different talk to Sami's because it's more like a higher level vision statement, and I will mention a few papers very flightingly, more on that basically give just a few samples on trying to convince you that auto-formalization is a realistic goal, and it's getting closer by the day. So what is this? So first idea of making mathematics really rigorous was the first recorded idea that we know about is Euclid's Elements, and this is one of the most published books ever, like after the Bible. And so this was very rigorous for its time. And of course, Euclid didn't know that you can just define things, so he try to actually make actual definitions for points and lines and stuff like that, which didn't make that much sense. But after that, he made very rigorous arguments, first time in the history of mathematics. But it's still not what I mean by formal mathematics. So the second big attempt at formalizing mathematics was by Whitehead and Russell, early 20th century, where they really tried to make it as a kind of a computational process. But at that time, there was no concept of what is computation. So they had these super tedious arguments, like 1 plus 1 equals 2, like 30 pages and stuff like that. And then people try to first make it clear what is at least logic. What do we mean by logic, and what is computation? And it was in the early 30s when Gödel and Turing and Church were working on these ideas. And of course, Gödel has actually not just an incompleteness theorem, but a completeness theorem, which for the first time said that whatever is, that there is what is semantically correct can be argued about almost always. And then people try the first attempt at formalizing mathematics was very early in the computer era, even before the first transistors became prevalent. There were already formalization attempts. And then in 56. So actually, there is a very funny statement from some workshop from 54 or so, McCarthy, where they said, OK, formalizing mathematics or creating a mathematician AI is like just a few months away. So that was 54. So then people started to just, OK, let's do formal theorem provers, and there were a few attempts, like in the 60s and 70s, and Mizar is actually still a living project, but it's very ancient, looking for the time it's Pascal and closed source and stuff like that. So basically today you can actually write formal proofs that can be checked by a computer. So that's what I mean by formal. So there's a big difference between formal and informal mathematics. A lot of things that people consider as formal is actually informal. This is just a text for humans, and it's not possible to check it 100%. But this proof that is on this slide is it's a Lean code. So Lean can check it 100% whether it's correct or not. And that has really big implications for mathematics. or for AI, sorry. So let's see why. So basically, formal reasoning is something that has 100% correctness that can be computer checked. It's fully specified and suitable for even verifying software. So in informal reasoning, it's kind of something that people might consider formal in some circumstances, but it's not. Its semantics is somewhat fuzzy. The problem formulation might be fuzzy. And it's most of the mathematics that is written in books and papers, everything. It's informal mathematics. It's not that you can just run a computer program on them and say which paper is correct or not. On the other hand, we are evaluating AI systems on these benchmarks. So MAS, GSM-8K, etc. These reasoning benchmarks, they are actually natural language understanding benchmarks as well. They are not really that formal. And there are a few formal reasoning benchmarks, but they are not very prevalent, and not many people use them. On the other hand, formal reasoning doesn't have enough data. So informal reasoning has a lot of textbooks, a lot of papers, millions of papers, tens of thousands of textbooks. And also, the problem, so basically what you can see is that you need a microscope to see all of the formal mathematics if you compare the amount of data in informal mathematics compared to formal mathematics. Although there are like something like you can see there are a lot of different theorem provers, but each of them has only a small fraction of formalized mathematics, and each of them is tiny compared to all the informal mathematics that wouldn't even fit on this slide if you would look the right scales. Okay, so that actually begs the question, why do I care at all? What is this all about? So why do I want to do mathematics? Or do we just want to solve some crazy problems that people care about for some reason that we don't know why? Like, who cares if the Collatz conjecture is true or not, or the Goldbach conjecture? So what I call mathematics is somewhat different that most people would call mathematics. So to me, mathematics is anything that can be formally run in a computer and can be verified. So that is my definition of mathematics. So basically, for example, let me just give a few, examples of mathematics is like, what is the best chess position in a game? Or in a poker game, what is the hand that is the most likely to win? Or what are the type annotation I have to add to a program to type check it? Or does this program ever throw an exception? These are all mathematics in my book, because you can write it in a formal mathematical statement, and you can verify it. And if you verified it, then you are done, if you're 100% sure. So in this case, it looks very general, what I consider mathematics. But what are the non-mathematics if these are all mathematics? So for example, in my book, non-mathematics is like self-driving, something that interacts with the world, and you cannot formalize. You cannot put in formal statements. Or it's not clear whether you put completely formalized self-driving or not. It's always changing. It has to do with natural world. Or what would a user enjoy? What kind of content? A lot of money is in that state question, but you cannot formalize it. Or is there life on the moon, Europa? Or something like robotics or cure for cancer. These are not mathematics. But a lot of other statements are, whenever you can formalize it and put it in some formal mathematical statement, logical statements, and it becomes mathematics. So is that the other question that other people ask, is that the mathematics nothing else but just computation? So where do I draw the line between mathematics and computation? If anything I can put in a computer and verify, then it becomes mathematics. So I thought a bit about it. So first of all, okay, what is computation? In that question, so if you want to draw a line, we have to specify what is computation. Fortunately, this is well specified, so everybody learns it in first year of computer science. It's a Turing machine or Church or lambda calculus. Both defines the same kind of computation. So it's basically a computation is that based on local changes using well-defined rules, but on arbitrary size objects. So that's what I call computation. So Turing machine does the same. You don't even have to use Turing machine. You can use some simpler model of computation. I made up this model of computation like a few weeks ago. It's a kind of Turing machine, but it's much easier to put in you can write it in 2 lines of Python code. So anything that you can do with a Turing machine is like you can do in this computation model as well. So what is then formalization? So formalization requires a verifier. A verifier is a Turing machine. And I still want something that this verifier does. So it's basically, it becomes logic in a sense. So what I want is a theorem proving basically has to have that statement should have negations. And so and either the negation or the statement should be verifiable. Not either one of, I mean, at most one of them. Sometimes you cannot verify either of them. So that's actually the Turing's halting problem. So Turing has proven that it's not always possible. But the negation should always be exclusive with the statement. And what is the semantics of logic? And then it's basically what we really want to have semantics is that for each Turing machine and each input, you should be able to have a statement that this Turing machine produces this output. And I still want a third thing, is that sometimes I should be able to say whether a Turing machine ever stops or not. Sorry, that's my I just stopped. Yeah, that's good. I stopped. Yeah, sorry. So yeah, basically, that's all I want from a logic. And then basically what I want an AI system shouldn't care about logic. So basically, what I'm saying here is that sometimes my logic should be strong enough to say whether a Turing machine never stops. Not for all Turing machines, but for some Turing machines. And it should be consistent with how Turing machines work. It should really only say for Turing machines that they never stop when it never stops. Okay. So that's my definition. And then if I have such a logic and such a model of computation, I just want my AI to cope in this environment. So basically the system that we want to envision, it shouldn't depend on first order logic or higher order logic or dependent types or whatever, homotopy type theory or whatever. Don't care about all that. All of them are just like particular instances of this thing. And what I want is my AI system works with these kind of statements, and it should produce consistent outputs that verify. OK. So why do we care? So why is formal or informal? So that's getting interesting nowadays because more and more people look, OK, we look at all these chatbots and whatever, and they start to say more and more interesting things. So they're getting better and better at emulating human outputs. So for example, at XAI, when we had our first Grok trained, then I measured it on some Hungarian high school finals, and it passed the high school finals. And not with the same grade as GPT-4, but 1 grade less. But still, it's pretty good so chatbots couldn't pass the high school finals 2-3 years ago, and now they can. So that's pretty interesting. So the progress is very fast in that respect. But that's informal mathematics. That's not formal mathematics. So why do I care that it's formal? So basically, the main thing what I believe is that you can push this kind of informal mathematics to a certain level when humans can judge the quality and you do some feedback and RLHF. But if you want to really bootstrap it to the absolute maximum extent, you want to have like a real reward, and the reward should be really correctness. And if you want to push it to the level that the best human mathematicians do without slowing it down by needing human raters, then you need a formal system to verify results. So that's the vision of auto-formalization that I'm proposing. So I use the same slide like in 2016, and it's still believe in this, is that what we really need is that we have a large informal corpus. We would like to have a language model that transforms the informal statements into formal statements, verify them, and then use that verification as a feedback mechanism to decide whether the statements are correctly formalized. So basically, imagine that these formal theorem provers basically create computer code for mathematics. So you want to build like a huge code base of mathematics using language models that translate between formal and informal mathematics, and at the same time they produce proofs. So I mean, it looks like a very high bar, so it looks a very ambitious goal, but I don't think it's getting less and less ambitious looking. So some people now say, that's almost trivial now. What's the problem? So it's like, basically there are two kinds of people. One kind of people say, okay, this will happen automatically, like Ilya Sutskever would say that. And some people will say this will never happen in this century. So I want to convince you that there is a chance that it will happen. So why this is good? Because if we have like informal mathematics, we have a lot of data, no grounding. We have the formal mathematics with little data, but very grounded. And we want to basically connect these two by having this feedback mechanism that does both formalization and auto-formalization. Oh, shit. Okay. And, oh yeah, that one. Okay. So let's look at what can language models already do. And that was an idea that was mostly like suggested by Albert and Tony. So basically, yeah. So I was just joking today, by the way, with Tony. I was chatting. He's Yuval Wu, actually. I think I forgot his name on this paper. So sorry. Yeah, so I think it might have copied. So actually Tony is in both papers. Yeah. There. So I was joking with Tony because Tony, Yuval Wu is actually that I didn't put. So I think I copied this slide from him. So that's why So Tony is like Semi already mentioned one of Tony's paper on length generalization, and he's also on the alpha geometry paper, and he's on most of the papers that I'm mentioning. So I was telling Tony that he should be the only speaker here today. But yeah, so basically this auto-formalization with large language model, we just tried, okay, can language models actually do, how far can they formalize things if we ask them to write link code? And it turns out, okay, they can do actually a lot. So language models can actually translate a lot of like basic high school level statements to Lean, but they make a lot of fundamental stupid mistakes. But they are not too bad, and sometimes the mistakes can be fixed relatively easily. For example, like here you get a statement like formalize a function, and it's very much natural language, and it turns it into a reasonable. Actually, it's Isabelle code. Sorry, it's not Lin code, but yeah. So this was done with different kind of provers. So different kind of models. Sorry, different kind of models. So each of them translates to Isabelle, and then so they were tried with Codex and Palm. And now we of course we're using Rocket XAI now, but other people use GPT-4 and others. Sorry. So what I really, so this is, for example, a relatively simple example, and it works pretty well. And this is also kind of wow, because it's extremely informal, and then it's even formalizes better than I would. So You have to really understand what it means, like tables and rows and whatever, and then it turns into modular arithmetic. And then, so this here makes a mistake where it hallucinates a function that doesn't exist, like more like a proposition, so that linear doesn't exist in Isabelle. But if you give a one-shot example of like some other example that just mentions a line instead of linear, then it suddenly doesn't use a hallucinated proposition, but actually inlines the definition of linear into the statement. So that's very promising. So yeah, so these language models make mistakes, but these mistakes are getting, suddenly things starts to work. So that's basically the story. And then we measured how many of these statements could be translated from math, which is a middle level exam data set, so it uses mostly high school level math. And it's kind of 40%, but it's not zero. So getting from away from zero is the big step. Now it's only the question of increasing the numbers. And I'm pretty sure that the current models are much better than this. So now, what about proofs? So we just talked about statement. Okay, it should be gone. So basically, proofs that's a very interesting result that basically says that if you want to, it compares what happens if you, so previous proof automation tries to use a combinatorial procedure to prove statements. And here the idea is very different. It says that, OK, first take a formal statement, informalize its proof, create an informal proof, and turn it back into a verified formalized proof. So it's kind of extremely different from anything that anybody did before. So it's a proof automation method that goes first to natural language, then does the proof sketch in natural language, then goes back to formal mathematics. And so it requires a certain style of proofs. So Isabelle has a certain declarative style of proofs that works well, and it's basically, and they do some search as well when they formalize back. So basically, they try to fill in the holes in the informal proofs by searching a bit. But generally, they got very so much better results than actual proof automation, that existing proof automation that people honed for years or decades, actually. So, and it's even with this method, it solves a few IMO problems. So, and it was a relatively, this is a year-old slide, so it's from last year, and the models were much weaker than today. So basically, that shows that there is a promise in auto-formalization. So we can go both ways. We can formalize and informalize. And both of them works to some extent already. Sorry. So, OK, and then I come to the last question mark on why is it hard to do reasoning with. So why is it so hard to accomplish the full vision? I think is that reasoning is just one part of the problem. When a mathematician goes and thinks about the problem first, you look at the whole literature. You don't just try to argue in some, and then try various random arguments. You go there and look at, OK, what's there? What are all the statements I can use? And that's called the premise selection. So often, if you find the right statement to use, then you're already done. Or the task becomes much easier. And that's a path that we explored very early on in 2016 in this premise selection, but I still think it's one of the most important, or maybe the most important problem. And it's basically we just contrastively trained an embedding model and looked at how we can rank the premises and then pass them to a formal theorem prover. And we could get much better proving rate by this simple method than previous premise selection methods. And this is the latest iteration with transformers applied to Isabelle. And why did we use Isabelle, not Lean, is that Isabelle has one of the strongest proof automation, the sledgehammer. And basically what we looked at is, can we expand this method to Isabelle? And would that method be at all competitive with the previous best proof automation, which was developed for 20 years roughly? So that's a poorly engineered solution. And the idea here is we do first like a contrastive training on existing premises, then we do ranking using this embedding model, and then we also re-rank the results using another transformer model. Here is the algorithm. I think it's not so important, but the funny thing is that, it outperforms sledgehammer by like 50% proof rate. So basically you can, so the sledgehammer is typically used by people who formalize statements, but they don't want to prove the simplest things by hand. So you just say sledgehammer, and then it will try to solve you. So now you don't have to mess with like the statements you can solve automatically is increasing by 50% if you use this. And if you use it with another like neural search method, then you can increase that proof rate by another 10%. So from 60 to 70. So this is pretty interesting. So it shows that neural methods really can actually, in the real life work of people who actually use these CNN provers, can save a lot of work, because these are very tedious things to do it by hand completely. And the best results you typically get if you, Mini-F2F is another benchmark that's relatively tough. And you get the best result if you combine this Magnus Hammer with DSP, the previous version that I showed that actually informalizes the statements and then the proofs, and then formalizes them back. So I think it's extremely funny because it goes against any conventional wisdom. So it's like, it's a completely new paradigm. Like, I think 2 years ago, nobody would have believed that. I had a hard time believing this, yeah. And the other good thing about this thing is that the scalability is much better than sledgehammer. So previous proof automation typically, so these are engineered methods. It's similar to early computer vision where they developed all these features by hand, that if you throw more compute at it, you get more gains. So it doesn't level off as quickly as combinatorial search method. They hit a wall and then they flatline. But that's not the same for neural methods. And also, it nicely scales with the number of parameters as well. So let me get back to the conclusion. So basically, I just wanted to show that this diagram is not as crazy as it looks. So we have measured like various aspects of it, like is it possible at all to translate from informal to formal and back? Is it possible to use neural network and transformers to prove things, even in real life scenarios, even on large code bases of proofs? And yes, we don't have a full system that does everything, but we have like almost all the lines have some proof of concept. Almost all the arrows have some proof of concept solutions already. And the question is, how do we scale up? How do we improve them so that this feedback loop is established, and then it can applied on all of mathematics automatically without any human intervention. So that's the dream. So what are the challenges? So we have like, we probably need long-term, so complicated statements we cannot handle, like that requires a long-term planning, and we don't know whether it will scale up to that or not. But we can expect it to some extent because we know that AlphaZero and other like systems could automatically learn planning without have been engineered for that by just using standard RL. So retrieval, we know how to do retrieval, and that's a relatively proven thing. We don't really know how to use experience. Like mathematicians also use their experience to derive statements, not just like just do like formal mathematics, but they also run like actual evaluations. Conjecturing is something that is underexplored, and also synthesizing definitions and concepts is somewhat understood now. And what I think is the hardest part, and that's probably the key to all intelligence, is this finding these hidden connections between faraway areas, because that's something you cannot learn by contrastive learning, because you don't know what is actually useful before you see it being useful. So for example, like the Fermat theorem relies on some really crazy hidden connection between elliptic curves and that equation. So it's basically very, very strange. And how do you find that connection? We are not sure whether neural networks find it. But we definitely see that neural networks are capable of translating, understanding natural language statements and natural language text and translate it to formal. So that's where I think is like the biggest challenges are, basically the planning and the faraway connection, hidden connection. So that's where I'm a bit uncertain about. But other than that, I think we are getting closer to this vision of reading all of mathematics and formalizing it completely automatically. Yeah. Thanks.
Very interesting talk. So the previous talk talked about classifying which problems could actually be solved with a certain technique or could be learned with a certain techniques and which ones could not. In this case here, you say that, okay, the automatic formalization works for a certain percentage of problems. Do you have some idea for which ones it works well and which ones it doesn't work well?
Yeah, I mean, typically it's, what we don't see much is if you need to define a lot of new definitions, because it's hard to get definitions right or check them whether they're correct. So you get much more signal for saying, okay, this formalization of this statement is likely incorrect or correct. For example, if it's syntactically correct or it's just not true, or it's not useful in the same context as the informal statement was useful. But you don't get the same immediate feedback for definition formalization. But it's much easier to derive definitions from actual statements than most people think. So for example, if you want to create the concept of rings, you just have to forget some facts about natural numbers. And then you get rings. So I think it's like creating abstractions is much easier than most people think. But formalizing existing definitions is much harder.
So thank you for the really interesting talk. So I have two quick questions. The first one is, how does your approach compares to other approaches that were recently proposed? I know OpenAI and Ilya Sutskever and Paul had this GPTF, and is there any kind of connections on the?
Yeah. So GPTF is also they tried for. So basically, I think the main difference is that they don't have an overarching vision on how to scale up and how to create a feedback loop. So they try to address like point problems, but they just like say, okay, focus on this isolated problem or that isolated problem. Where I say, okay, is there a path so that we can create an absolutely automated system that can handle everything? And what that path is, I mean, when I'm working on various problems or working with others to inspire them to write some papers, then I'm typically trying to first get the framework so that if this and this and this is solved, then we have a feedback loop. Then we can do kind of like an AlphaZero for mathematics. or not alpha 0 because we want to formalize. So basically, we have still a lot of human feedback. But it wouldn't require actual human feedback. It doesn't require mathematicians that goes in and checks whether the correctness of a problem is, that the correctness of a solution is really there. So what I really care about, and this vision is like, I first, so actually my first white paper on this was 2013 at Google. And I didn't change much because I think that this is the most likely path that will lead to really an engine that reliably understands everything and demonstrates its understanding. And I'm just putting all the pieces into that framework. I don't care so much about this particular or that particular proof rate alone.
Okay. And I guess the other thing is you mentioned the advantage of Isabelle, but also there is obviously now this growing lean community.
Yeah.
So in terms of training data, is it advantageous to basically try with like formal verification where the community is bigger so that you get better training?
Yeah, that's my only criteria. What I was saying is that I don't really care about the logic. So I only think I care about the logic is that it can make statements about certain Turing machine never halting, basically. So anything else, and most logic does that to some extent, or slightly better or worse than others. But if some system like first-order logic is already kind of Turing complete, that you can actually embed almost any logic into first-order logic, that it's like it simulates, describe that logic. So basically, you have like kind of a Turing equivalence between logics as well. Like, so if your logic just has a minimal requirements, then it's a good enough logic. Then it's only considerations of how much training data you have in that particular framework. And Lean is now a winning candidate, in my opinion. Yeah.
Thank you.
More questions?
So large language models are very better at informalizing than formalizing. And do you think that doing back translation is scalable or not?
Absolutely, back translation is one of the ways that the whole thing should work or could work or is work. So yeah, that's what I'm currently doing. That's why we are doing a lot of informalizations, because we want to do back form. So cycle consistency training is a very good idea, and I think that will be an important component. Yeah.
Thanks.
Thank you for the talk.
Hey.
And very exciting to see further progress in this field in an overview. I'm wondering if you have any thoughts in the medium term, how could this and should this affect the way we produce scientific knowledge, for example, in mathematics, in computer science, and so on, and how we access it, right? So given that if we can go to between formal and informal, how should we produce the new results that contribute to this body of knowledge?
Yeah, so I mean, there are different visions by different people. So what I imagine is that AI is developing much faster than humans learn new technologies. So we will have AIs adapting to people in the next few years. And basically, humans will interact, or researchers will interact with AI systems mostly in natural language. And you might inspect formalizations, etc., but you have to write less and less formalizations. But the formalization, but there will be an increasing amount of formalization in the background. But the human, basically what I imagine is that when this whole thing is finished, then you interact with an AI system the same way you interact with a colleague. So mostly natural language, and sometimes sprinkle in some formalizations, maybe if it's getting very technical. But it will be more like a very organic experience, rather than the current experience is that you either go extremely organic and you just talk to colleagues, or you just go in and program all day in a theorem prover. I think this will be much more going that the computers will adapt to you, and you just interact with them mostly in natural language. Yeah.
So there's a connection between mathematical proofs that are formalized and computer programs in general, right? And how is learning to prove easier than learning to code in general?
Okay, so I mean, it's not okay. So there is a very theoretical equivalence between proving and programming, the Curry-Howard isomorphism, which is not super practical and nobody really uses it in practice. Okay, so
but aren't theorem provers using this?
Yeah, in theory, in the background, there's a kind of like a design principle for the logic, but not that explicitly that. So you don't look at those things as a programs per se too much. So that's not the purpose. But yeah, I mean, I don't want to get like too philosophical here. I think there is certainly a connection, an explicit connection, and there are more implicit connections. Like these are all computer programs as well. So even so surely the thing is that if you want to learn to program, in my opinion, the problem is that the most programs that people look at are relatively shallow and ad hoc. So for example, go look at a text preparation program. It's super complicated, but not very difficult. It's more like a lot of shallow computations, but very ad hoc computations. So, but mathematics is very rigid. So if you have a lot of consistency and a big depth, and it's easier to bootstrap this because you have much more signal whether you formalized correctly or not. If you want to formalize something to a program, then you have much more freedom. You have to know much more about culture. You have to know about taxes, for example, or whatever you want to write a program for. So most of programming is about interfacing reality with processors. So that's hard. That's not as unique. Mathematics is much more rigid. So that's why I think auto-formalizing all of mathematics as a start is much more realistic than learning to program in this really wide variety of things that are relatively sloppy. So that's my intuition. But yeah, the two are very connected. And I think once you have this super strong reasoner, you can use it for a lot of like programming verification and other stuff, which I think will be very important for programming as well. So I don't think that program synthesis can work without verification in the long run. So.
Thank you.
Okay, one more. Sorry.
Hello. So you mentioned that there is not enough formal data for doing auto-formalization, and whereas like there's tons of like informal data. So to be able to learn an auto-formalization system, we need a parallel data between informal data and formal proofs, basically. So and the amount of people that understands and know these languages, formal languages, is very small. So the data collection pipelines are not very scalable. So do you have any suggestions for that?
Yes, so basically my suggestion is auto-formalization. So, so I think that actually parallel corpus is much less important than most people think because neural networks are pretty good. So surprisingly good. Transformers are surprisingly good at actually connecting things. The problem is the overall amount of formalized data. So basically we don't have a lot of concepts formalized, like a lot of definitions are missing. And that's the real problem. But I think that could be bootstrapped with a loop, what I'm saying. So basically, you want a system that formalizes with less and less human intervention and formalizes it more and more and faster, and then it builds its own code base by itself. So that's That's where this whole idea is coming from. So I don't really think it's like we have to have like a full translation of everything, because if you have that, then you are done anyways. Then you formalized all of mathematics. So that's not feasible. So I think is that we want to have an AI that actually formalizes things, and then if it notices that it screwed up some part of the formalization, it starts again, and then redoes it until it fits well enough with the informal data so that the matching is there. So that's what I think is realistic. Yeah.
All right, so let's thanks again, Christian. And we have a 25 minutes break. We come back in. So welcome back. Can you hear me? I'll just borrow your microphone.
Oh, okay.
Oh, you can keep it. I'll just take the... Yeah. And if you can... All right, so the next speaker is Teng Luong. Teng is a senior research scientist at Google DeepMind, ex-Google Brain. And he obtained his PhD in Stanford University in computer science in 2016. At Google, he built many of the state-of-the-art models, both in language and vision. He co-founded Mina, which became the well-known Lambda. And now he's co-leading the development of BART multimodal at Google, and is also the principal investigator of the recent breakthrough on Olympiads with alpha geometry that he will talk about now. So welcome, Teng.
Thank you. Okay, yeah. Okay, yeah, thank you, Emmanuel. Thank you, Sammy, for inviting me to the workshop. Thanks, everyone, for joining. So I'm going to talk about alpha geometry, and I also touch a little bit on advanced reasoning, and then think about the future a little bit. So, you know, we have been having tremendous progress in AI. We have ChatGPT, Bard, Gemini. It can help you do awesome things. For example, write email to your boss asking for a raise, or it can, write a poem to your wife, your lovers. But why math now? Maybe one simple answer is because you can be quite rich. If you can build an AI that can win an IMO gold medal with open source, it can just read informal text and then produce informal proof, then you can get $10 million. So that's the new AIMO that just came out last year, or actually this year. But I think, joke aside, for me, math is quite exciting. I think math implies that you have to really think for a long horizon. You have to plan ahead. You have to see the big picture. You have to make sure everything connects. And I think that actually means that it's about advanced reasoning. And I was trying to play around with ChatGPT last night. I want to find silly mistake of ChatGPT so that I can show some nice result from Gemini. But it turns out that ChatGPT is actually quite good. I was I was given a triangle ABC equal to triangle XYZ. I want to trick it. I say, okay, let's rotate ABC clockwise 30 degrees, XYZ counterclockwise 60 degrees. Are the two triangles still equal? Well, it turns out, it can answer very well. It can reason that, transformation, rotation, will still maintain the congruent properties of these two triangles, so they still equal no matter how you rotate, translate them. Even if you ask them, are the triangle ZYX equals CBA, it can still do very well. But I think if you start to ask a little bit more difficult questions, you have two equal triangle ABC, you take the two midpoint D and E of AB and AC, you take the two midpoints of XY and XZ, which is M and N. So RDE parallel to MN. So if you read through the solution, the answer, so it was saying something very correct, like D parallel to BC, which everyone's familiar with. D is half of BC. And MN is parallel to YZ, and MN is half of YZ. But then it's at the very end, it starts to make this, this implication, this thinking. We have D parallel to BC, we have BC equal to YZ, we have YZ parallel to MN, and then now we can think that D is parallel to MN, which is obviously not correct, right? Because these are just
triangle, so it can be in any order. So talking about math, I think everyone probably familiar, for sure, probably heard about the IMO. So this is the most prestigious math competition in the world for high school students. So it has been it has 100+ countries. So oftentimes you have 2 days. Actually, it's always like that. There's 2 days. Every day, each contestant have to solve 3 problems for 4.5 hours. So problem 1 and 4 are easy. Problem 2 and 5 are medium hard, and problem 3 and 6 are really hard. So I think if you can solve the first 4 problems, 1, 4, 2, 5, and then if you get some partial credit for problem 3 and 6, then you can get a gold medal. So I think that's probably one. If you want to win the AIMO, you can have some strategy like that. But I think for us, if we can solve math at the IMO level, that means I think we're on the path towards the kind of being able to master the reasonings capabilities, and that's why we look at solving Olympiad geometry, and also because in the IMO there's 4 categories: geometry, algebra, number theory, and combinatoric. And obviously geometry is probably the easiest topics, which is why we tackle that. And by the way, this is the work with a trio: Tony, Kwok, He, and me. And we want to solve it, but we don't want to make use of any human example. So this is like learning in type of some scratch without any human examples. So this is actually it is the well, okay. Actually, yeah. How can we skip that? So I just want to tell you this story. So there's very famous pupil, Le Bach Anh Trinh. He's actually quite well known in Vietnam. He's my Olympiad math coach in high school. I was doing full-time math, Olympiad math during high school. I got to the top 8 in the country, but didn't make it to the top 6 to go to the IMO. So then I stopped doing math for 20 years until recently. But I think Le Bach Anh Trinh, he actually glorified Vietnam 40 years ago. So in the IMO 1979, he ranked number 1 in that year. And he got the special prize that year because he was able to solve this problem 3. You just learned that this is a hard problem. And that is a geometry problem. And his solution, it was so much elegant and actually unexpected, much better than the organizer solution. So they use his solution as the correct answer. And it's very simple. So I can tell you, so there are 2 circles here, C1 and C2. So there are 2 points M1, M2. They start from the point A, and then they go with the same velocity. So they meet again at point A after 1 round. So there's a question, is this proof that there is a point in the plane? So that at any point, any time when the 2 points travel, that point have equal distance into point M1 and M2. And the proof is actually quite elegant. If you call B is the second intersection point, we get we cross BO1, cut the circle at B1, and BO2 cut the other circle at B2. And let's call P is the middle point of B1 and B2. That's the point that has that property that at any point in time, PM and PM1 and PM2 are equal. Because we have PM1 is parallel to B2, M2 here, and they're equal angle. So 2 middle points would also parallel, and they always have equal distance. So I want to do a quick game for you. Let's make a guess. Any of you think that alpha geometry can solve this problem? Raise your hand. Okay, a few, not everyone. Okay, so hold your thought. I'll give you the answer at the end of the talk. So in a nutshell, what is alpha geometry? So alpha geometry is a neurosymbolic solver. So I'll give you an example. So we have a triangle ABC, and AB is equal to AC. And we want to prove that the angle ABC here is equal to the angle ACB. So the way alpha geometry works is that we first send it into a symbolic engine. If it can solve it, that's great. If it can't solve, then we're going to go and ask the language model, give me some suggestion, give me some idea on how to solve it. Give me some magic construction, we call it rabbit, pulling out the rabbit out of the hat. Yeah, we ask for help, and then if we can't solve, we keep asking for the help a few rounds until we can solve it. And in this case, when we ask the language model, it gives us some construction, which is point D. If we construct the point D here, we can then have like AB equal to AC. We have BD equal to DC, and then we have the common edge here, which means the two triangle ABD equal to ACD. And then you can derive that, this is your familiar problem in secondary school. So neurosymbolic solver, actually, we was inspired by system 1 and system 2 in the sense that Neuro is actually very fast, creative, but actually not quite reliable. On the other hand, system 2 is a symbolic engine. It's not that creative, but it can be reliable. So once you know the correct points and line to add, then it can solve the rest of the problems. So let's take a look at a more advanced example. So this is one problem in the IMO 2018, problem 1. I'm not going into detail that problem, but basically, we need to prove that the line DE is parallel to the line FG. And if we somehow can get the magic construction, being that we get the M is the midpoint of line AB, N is the midpoint of line AC, then everything becomes easier. Then you can just let your symbolic engine to do the probably slightly boring work for you. So you can have like MN parallel to DE, MN parallel to GF, and then that leads to DE parallel to GF. So the question here is, how do we teach LM to have that kind of magic construction? You can think of magic construction here as a kind of like insight, the kind of idea, key idea of solving a hard math problem. So how do we do that? So if you remember your secondary school, high school time, when we learn geometry, we often maybe take a paper and a pen, we draw some random figures, and then we learn some properties, and then from that we understand geometry better. So we were inspired by that kind of knowledge building process, similar to humans. So the key here is we don't have a lot of human training data. Large language model trained with a gigantic amount of data, but I think for math, especially Olympiad math, it's very hard to find a lot of data like that. So we resort to the syntactic data generation, and we do that at scale. So these are the examples of the kind of random diagram that we explore. And let me tell you in more detail how we do that. So this is one random diagram. And then given that random diagram, that gives you a few leaf node here that we're starting from. And then from the leaf node, we start to expand. We have the rule set. We start to expand the rule set to connect the leaf node to derive new node. And each of the nodes there will be one theorem and proof. For example, you can see one node here, cyclic EADH. So that's one example. So that's one theorem and proof. And then you can have more complicated one here. So it will lead to this is the property HA is perpendicular to BC. So one node will include both the theorem and the proof. And then we have to trace back, to go back and then figure out which part belongs to the theorem, which part belongs to the proof. But I think this is a big picture. And then I'll give you a specific example how to do that. So these are the leaf node AB equal to BC. Then we can have a basic rule, a transitivity rule, right? So we can derive that A also equal to C. So this is one theorem we can derive, which is let A equal to B, B equal to C, prove that A equal to C. So this is how we start from the tree, we turn it into a sequence, so we can train a language model. So the language model operates on the string. Yeah. But to be clear, it's not this kind of natural language. We have our own domain-specific language. Not Lean either, because I think Lean is very hard to formalize geometry, which is why people couldn't make progress in geometry. So one of the first author, Trio, he spent like 2 years in NYU, came up with the language, the domain-specific language for geometry. And when we met at Google, the first thing I asked him about that problem 1979, whether we can solve it or not. And then from that, we were motivated. We want to scale things up at Google. And that's what led to alpha geometry. So here's a more specific example that you see. So AB equal to AC, and then DB equal to DC. We know that D is on the same line as BC. So then from this, we can derive that the triangle equal, there's a mistake here. This is triangle ABD equal to triangle ACD. And then we can derive that this angle are equal. So given this tree, you can also serialize. You can also have this theorem here. But if you read for a second, they're actually quite a boring theorem because you are given everything. So ABC with AB equal to AC. We also given this midpoint BC. So it's actually quite a trivial problem because this part here is not necessary for the theorem because the point D here, the point D is not appear in the proof at all. So actually it's not necessary for the theorem. It's only necessary for the proof. So how do we make it more interesting? So I think the trick here actually try to move that part to the proof. So now you can see that the theorem now is actually more interesting because it hides away the part about the point D. So the point D here actually come into the proof. And this is the kind of insight that we want the model to learn, to generate. I mean, if you can try to think about LLM, right, you can also try to, like generate some hidden proof. You move it into the output, and then you teach it how to produce those kind of outputs. So this is sort of kind of insight that we want to teach the model to think before solving. And this is one example of such thinking. We think about what are the magic construction. So the magic construction here, the point, the D middle point. So how do we identify this magic? This magic construction. So going back to the previous tree, right? We build this tree. So once we build this tree, so the final node here is the goal. We can go back and we can do construction, conclusion, traceback. We have all of these leaf nodes here that belong to the conclusion. So we also can do what we call object traceback, meaning that we look at the object in this final goal here. The object includes the 3 points, A, B, and C. There are 3 objects here. And these objects only relate to this leaf node, AB equal to AC. But it doesn't relate to these leaf nodes. So then if you subtract away these 2 sets, then you actually ended up with this part here, which is a magic construction. So these leaf nodes doesn't have to be in the theorem, but it's actually important for the proof. So this is how we can identify the kind of critical insight in the proof. And then so these are the magic constructions that we will train the LLM to predict. Is that clear for everyone? I think this is probably an important slide, the most technical one, I guess. I'll give you a minute to take a look at it. I think it's actually an interesting idea that maybe generalized to other domains. But of course, there's a catch to it, right? When we said it can be applicable to all domains, but it's not trivial if you want to go from geometry into a different domain. For many reasons. Even the first reason, building domain-specific language and deduction rule, it took the first author 2 years, and then another 2 years, we scaled this thing at Google. So actually quite a bit of work. And then you also need to have, we were lucky there's a symbolic engine exists, the DD part. We upgrade it into DDAR, You also have to do like, you know, some minimum spanning tree to do conclusion traceback, and then you also do more work to do object traceback. So it's a good recipe, but actually a non-trivial one. So you know, we don't want to claim that this is going to apply to all other domains right away. It might take, you know, quite some work. About the data, so you know, like I remember like around the year 2020, like we have been iterating different versions of the data because our data is actually quite big. We look at 1 billion random diagrams, and then we let about 100,000 CPU workers just like deriving all the property for these random diagrams for 3 days. We got about 1 billion theorem proof. We did duplication. We got back to 100 million theorem proof. So this process is actually quite intense and also very easy to make mistakes as well. So I think around January 2022, where I think we got to version 8 or 9, something like that. By July, we got to version 9. That was the first time we got to solve some major geometry problems. And then I think very quickly, once we got the first major problem, then I think like October, we solved the first IMO problem, and then December 2022, we got to solve most of the IMO problems in the set. So it's quite exciting.
The 100 million were generated informally, the theorems and proofs, or in your formal language?
In our formal language. Yeah. But our formal language have a nice property that it can actually easily be translated into natural language. Yeah. Okay. And this is the distribution of the 100 million theorem and proof. So if you look at the x-axis, we order by proof length. So 1 would be something very trivial, you know, like the angle in this circle here is 90 degrees. And if you look at the proof length, which is like we have longer proof, maybe like 20 proof length, it started to discover familiar theorem. For example, this is the Euler circle, the 9-point circle, if you remember the secondary school geometry. And even crazy, up to like 247 length, we have proof like that. So it builds crazy diagram here, but at the end of the day, it asks you to prove that this angle equal to that angle. So crazy. But I think we did try to send some proof, some problem to like expert in the IMO, and they do think that some of these problems can actually be a real context problem. Well, and the way we find those problems is, for example, like we look at diagram where there could be a large amount of node, but then the proof length can be like short or something like that. So we have certain criteria. So among these 100 million examples, there's about 9% that have the auxiliary construction. So these are the kind of insight and thought that we want to teach the LLM. So we would return the LLM, like a sequence of tokens. It have the problems. Some example doesn't have the auxiliary construction, only have the proof. Some would have the problem, auxiliary construction, and then the proof. So we mix them together, and we just train the whole thing. And it's not the large language model, though. It only have 151 million parameters. It's a matrix transformer, 12 layers, A hat, 1K embedding dimension, 4K hidden size. Vocabulary size very small, 757. Maximum context length is 1K. Most of the example less than 200 sequence length. We can make this a tiny amount of compute to train. So I think like TPU-v3 4x4. I think Sammy knows this architecture pretty well. So we pre-train for 10 million steps, and then we fine-tune for 1 million steps on the data with auxiliary construction. Yeah, clear? So here's the language, actually. So let me walk you through it a little bit. I think it's actually an interesting part that took quite some time. But that's the thing that enabled alpha geometry, actually. So if you look at the first, so this is the rule in alpha geometry. So this is like saying perpendicular. So we have the line AB perpendicular to CD, and then we have the line CD perpendicular to EF. and we know that ABA is not on the same line, we can derive that AB is parallel to EF, right? So AB perpendicular to CD, EF perpendicular to like CD, they parallel. Or you can have your familiar theorem, it's like E is the midpoint of AB, F is the midpoint of AC, so that the two midpoint EF parallel to the line BC in the triangle. So this is the DD part, which existed before. And Trio, the first author, extended it to have the algebraic reasoning as well. Because if you only do those rules, you can only prove properties like D3 points on the same line, D3 line intersect at the same point. But we cannot reason about like this angle equal to that angle. So to do that, we're going to use like the kind of like Gaussian elimination. You turn everything into like equation, and then we can perform derivation in terms of like the angles here. So we can derive at this angle like pi half 90 degrees, or we can derive that like certain edge equal to other edge. So this enables some like algebraic reasonings. And let me zoom out a little bit to give you the full picture of alpha geometry in action. So if we have a problem here in natural language, the first thing we have to do is actually we have to manually translate. So this, I think we need Kristen here, help here to do auto-formalization to turn into like natural language here into this is alpha geometry language. So this is the language that alpha geometry operates on, but then it's also very close to natural language. So it's something in between formal language and natural language. And once we can construct the solution, because it's in a natural, we can turn it into natural language. We can also send to expert for evaluation. And in fact, we did send to expert to create the solution of alpha geometry as well. So if we look at all geometry problems from the year 2000 until now, that like there are about 40 problems. Among those 40 problems, alpha geometry can formalize 30 problems. So we can handle about 70% of IMO geometry problems. So we call this data set IMO AG30. And among those 30 problems that alpha geometry can represent, it can solve 25 problems. And if you look at statistics of gold medalists, they can solve 25.9 problems. So we're very close, just one more problem to go to outperform the gold medalist. But also exciting that we outperform the previous Biot-Wu method. The average IMO contestants can solve about 15 problems. And if you look at the year 2015, so that year there are 2 geometry problems, and we were able to solve both of them. And if you can think of it, it can actually be equivalent to a bronze medal, winning a bronze medal at the IMO. I think we were lucky to got that. And in fact, we sent the solution to Evan Chung. He's a USA IMO coach, and he said that the solution were correct. So I think we are certified, So remember that P2 is really hard. It's a hard problem at the IMO. So like this diagram that tells you it's a hard problem. A lot of points here, a lot of circles. Even if you draw the diagram yourself, if you don't draw well, it can be very complex. It's very hard to see. So the solution that alpha geometry gave have 109 steps. It's a very long proof. But the nice thing about it is actually it's all basic rules. So if you're patient enough, you can read through and understand it. So it suggests things like construct D midpoint of BH. So BH is here. Construct G is midpoint of HC. HC is here. H is the intersection of the 3 altitude. And then it also construct point E midpoint of MK. MK is here. It's also figure out things like Euler circle. So we have the MO2 GD. So M here, O2 GD. This is Euler circle. Of course, to alpha geometry, it doesn't know that this is Euler circle, but I think through its proof, actually it's going through the property of Euler circle there. And then eventually it can say that these 3 points are on the same line. So we showed the solution to Alvin Chen, as I mentioned before, and actually I think it's quite impressive because verifiable, it's clean, it uses classical geometry rule, just the angle, similar triangle, just like students do. I also got a chance to meet Dr. Trinh Le I told you earlier in Vietnam last year, December. I saw this problem to him, and actually he was quite impressed because the fact that it can use only elementary rules. But actually, it's not really satisfying for him because he feels like there's no soul in the solution. Every time he look at the solution, he look for a big picture, something elegant, something that connect everything. He showed us that like you can actually can solve it in less than 20 steps if you use inverse geometry. You can easily map points in line, and you can get the right property nicely. And as I told you, right, if you don't draw the figure well, it can be very hard to see here. Yeah, so to answer your question, after many years, after a lot of work, we can still solve this problem. So this is why, because the way the language describes, first of all, it's about like 2-point traveling, right? So we need to approximate that a little bit. We can still do it, but then the question is about proving there exists a point, P, which we don't know what is that point P. And in alpha geometry language, everything has to be constructive. You have to be able to construct every single point in that diagram, and then at the end you will tell, okay, these 3 points are on the same line, these 3 lines intersect, which is why we still couldn't solve this problem. But hopefully, maybe like alpha geometry 2 or something like that. So in summary, I think there are 2 big ideas here in alpha geometry. I think number 1 is that we think syntactic data is actually quite important. And if you do it well, you can actually achieve great things. Of course, we're also lucky here, right? Because geometry is actually very specific. There's like only a certain number of objects, certain number of rules that we can construct. But I think if you start talking about combinatorics, it's just like all natural language, all the objects that human can describe, it's going to be very hard. So we were lucky with geometry. But there's also a second idea about language modeling, predicting the inside, which is the magic construction. And then from the inside that, then you can keep doing the search, and we're able to verify things. So I think we happen to have all this recipe in alpha geometry that like we have a symbolic engine that we can verify things. We have a language model that can predict magic construction. So you might ask like what beyond alpha geometry? I don't know what time. How much time do I have? 5 minutes. Okay. Oh, 5 minutes. Okay. Okay. Cool. Yeah. So obviously could be alpha geometry too. And right now I'm leading some effort, and we're going to extend beyond geometry to do other area of maths. And but I want to step back a little bit. I think this is my time with Sammy. We were doing Sammy was an endorsed this project Mina that I built back then. I founded this project back then. It was one of the best, probably the best chatbot in the world at the time. It's very close to human. So I would say around that time we were talking more about Turing test, But I would say I think Turing test is about imitating human, right? We try to imitate. But I would say we're at the position at the tipping point that I think there's AI format going to be posed for new breakthrough, new discovery. And we don't just want to imitate. We don't just want LLM to imitate the human knowledge. We actually want it to be able to discover, to find new rule, to find new breakthrough. And I think and this is what I just mentioned, right? We want to go beyond imitation test into discovery test. And I think math is probably one of the very good tests that we want to do. Because I think, as I mentioned earlier, I think math leads to advanced reasoning. And I believe that advanced reasoning is probably the key prerequisite to AGI. And I think with that, thank you. Thank you for your attention.
Thank you.
Yeah, thank you.
questions.
Thank you for the talk. So in the last Llama series, Meta said that they included a lot of code because it helped the LLM to do reasoning on even on natural language. Do you think that including such symbolic language in a large language model could help it like somehow generalize to other reasoning tasks?
So the question is, if we can maybe like train large language model further?
Yeah, so like include this kind of symbolic reasoning into the training data. Do you think it could improve the general reasoning ability?
Oh yeah. I think that's a very good point. I hope that it will be yes. Answer yes. I think like we know that, right? You know, if we retrain LLM with coding, it can actually like do reasoning or follow instruction very well. So I do really hope we haven't tried, but I think like I do really hope that like if it's also a nice thing that this data is in natural language as well, and then in the data there will be like proof steps. You will see derivation proof step 1, proof step 2, proof step n. So I hope that if we can actually pre-train on this data, maybe it can also make the model better at like multi-step reasoning. And I think we discussed about that, but we haven't had the time to try it. But good question.
Yeah, I was just wondering, because when you compare, so if I understand correctly, so this alpha geometry model has kind of this LLM that suggests some clever constructions, and then you just somehow brute force verify if with this construction you can prove the thing, right? So I was just wondering, so if you replace just the LLM part by a human, so a human suggests just a construction, and then you add the brute force parts behind. So how does it fare against human in this case? Because in some way it's kind of an unfair somehow comparison, because the IMO contestant also has to do the brute force part, right? Whereas in some way alpha geometry gets it for free, I guess.
So can you say the
so the question again? So the question was, so if you have you tried, for example, giving some humans the brute force part and telling them, okay, now you're allowed to add some constructions and see how well they do then? Because I feel that's a kind of more fair comparison to see how much the LLM is actually reasoning.
I see. Yeah, maybe I can answer the easiest part first. You know, we do look at problems that that alpha geometry can't solve, and then so it does. You know, sometimes if we give it like the oracle construction, it does happen to solve it. I think that's one aspect. There's also a different aspect is that like even if sometimes there's that problem where we give it like a correct construction, it can't solve it. It still can't derive at the end. Because I think we realize there are also missing rule in the rule set. For example, things like, you know, if you have like two circles intersect A, B, and then you have like, they also intersect like at the two other points, and then how do you infer that they all intersect at the same point or something like that? It doesn't, it has some missing rule. So I think that might touch some part of your points there.
No, I was just wondering if you give a human this kind of solver, maybe it gets much better in terms of like average score.
I see. So you're saying that what if the human have the solver, and what the human only need to do is to predict.
Right. Exactly. Yeah.
I think for sure. I think probably humans are pretty good, right? So for sure. Yeah. They will win for now.
Okay. So it does look only for geometric solutions, only for Euclidean geometric solutions.
Euclidean.
So it doesn't look like for coordinate or other ones.
Yeah, it's only Euclidean geometry.
Only like Euclidean, no, but I mean the solution's only in the style of Euclidean elements.
Right, that's right. Yeah.
There was some algebraic part.
That's right, but it's only the dry basic rule, like, you know, equal angle, the angle chasing, equal edge. Of course, like people.
Yeah, the problem we mentioned is much easier with complex numbers.
Oh yeah, for sure.
Complex numbers.
Oh yeah. I mean, before alpha geometry, right? people use computer algebra to solve a lot of these. But I think what we got attention from when we talk to people like Evan Jung, the coach, I think, or my teacher, they're impressed by the fact that it can be solved by just elementary rules.
It's here. So I have a question about the synthetic data. So more generally in other domains and learning too, when we use synthetic data to learn, the synthesizer, it has a specific set of rules and forward processes that can map, the input to output. But what happens is that in some fields it's common that only a subset of the synthesized data is interesting because only a subset is relevant to the real world and so on. And what happens is that the learner will fit to that distribution of synthetic data entirely, but if you can select somehow the subset that is relevant, often the performance is not necessarily as good as the general distribution, the synthesizer. So in the case of your 1 billion examples of synthesized, I suppose those geometric problems, they are not uniformly interesting, all of them, only a subset of them are interesting and so on. Maybe that's what they comment about, like having a soul in the, it's like there's some other aspects that are relevant. So do you see that generalization gap here too, or what subset of these are essentially something that beyond providing a proper learning example in terms of a premise and a goal and a proof, but would have actually more implications in terms of being relevant?
Yeah, so I guess like there's a few parts to your question. I guess the first part is like you asking like if there's like boring example or something like that, right? I think there are. Like if you look at this plot here, so like those that have like shorter proof step actually like boring examples. So there are a lot of them. So we did try different applications though. For example, if we use only 20% of the data, I think we can still solve like maybe 23 problems. There's still like missing 2 problems. And I think like the more you visit like data over here, it's also like this is a hard IMO problem here where the proof length is around this portion. So I think like these regime has more interesting problems. And when we when we fine tune on the problem that have auxiliary construction, these are more interesting problems because you need more actualized endpoint to prove it. So when we fine tune, well, if we do only pre-training, we can solve maybe like 23 problems. And then if we fine tune further, we then can solve 2 more, like 25. I guess maybe that touched some part of your problem. And of course, like if you talk about other areas like combinatoric, it would be really hard, right? We were lucky with geometry. There's only certain objects. There are only certain rules. And we make use of the symbolic engine during our data generation process. Is that we need to like, we can validate that we can derive all the properties from random points and lines. Does that answer your question?
Yeah. I guess like maybe there's like the length of a proof is a proxy for being hard, sure, yes. I understand, but in that sense, not necessarily every problem that has a lengthy proof, I mean, humans would find it hard, but it doesn't have equal relevance when it comes to anything beyond, just a game of,
it's just an approximation.
So but I don't know actually what is the other criteria for make a specific like geometric problem interesting or relevant other than what is the length of the proof of it. So that's why I was thinking there's another distribution other than the one that we can generate, which is like synthetic data generates that distribution, but there's a subset of them that would be more relevant. But I guess it's a longer discussion. I'll be happy to take it offline.
Yeah, we can take it offline. Thank you.
Thank you very much. I think to keep schedule, we will thank now again.
Yeah, thank you.
So the first speaker, it's Arjo Lotfi. Arjo?
Oh. Forget. Yeah, thank
Does this sound good? Okay, great. So I'm also going to talk about the reasoning capabilities of transformers. And we are going to introduce a locality barrier, which is a learning barrier, which may explain the difficulty of learning in some cases. And also introduce a new variant of the scratch path. This is a joint work with Emmanuel, Sami, Colin, and Omid. And it's also, as Emmanuel said, a part of a collaboration between Apple and our research group. So in the previous talks, you saw the results about some failures and some success cases of transformers and large language models in general. And I'm going to give you 2 more examples of failures. So first one is that we have 5 people. We give pairwise relationships of their heights comparison. And then we ask the model to kind of compose those relationships and compare two people that we didn't have the direct relationship between them. And as you can see in this example, the ChatGPT fails to do that for 5 people. And actually, we tested that in a more systematic manner, and it only can get 60% accuracy for 5 people. As another example, which is more related to math, we give 4 equivalency statements to the ChatGPT model, and we asked to kind of, again, to compose those statements. And first, it fails because of some math mistake. But actually, for this task, there is no reason to perform math. These are just combining the equivalences. So we ask it again to not do any math and just use the equivalency statements, and it fails again. So as a running example and as a kind of an important example, we consider deductive reasoning. Because deductive reasoning is an important sort of reasoning, and by that we mean that having statements like A gives B and B gives C, we want to infer that A gives C. And that's one of the most typical reasoning that we use in mathematics, and also maybe other kind of reasoning areas. And we can always kind of make this problem abstract and model it with a directed graph, and ask whether there is a path between 2 nodes or not. Particularly, we make it as simple as possible. So we have a graph, we have some edges, we give these edges to the model, as you can see. And for simplicity, we make sure that each vertex is just 1 token. So there is not that complication from parsing the tokens and so on. So it's like a fixed structure. And the output is 1 if the nodes are connected, and for example here A and M are connected, so output is 1, and otherwise the output is 0. And of course there are different things that can make this task more challenging or not. For example, the number of edges, because it makes the search space larger, or the distance between the nodes that we query, or the diameter of the graph. So as the first step, we used random graphs to kind of see what happens. So we took random graphs with 16 nodes and 30 edges, and we trained fine-tuned the GPT-2 model on this task to see what happens. And this is what happening. So this is what happens. So we can get very fast to an accuracy level of 80%, and then we kind of plateau around that region. But still 80% is a good accuracy because we also use the different distances. But we were wondering if the model has learned to kind of find the distance, find paths between the nodes, or is it just relying on some other correlations? And for that, we used another distribution. So instead of random graphs, another form of graphs. So it's the same problem, just the distribution is different. And we observed that it actually performs at a chance level on the new distribution. So even that in the new distribution, also the distance of the nodes is 2, for example. So it's not really learning the right thing, which is finding the path between 2 nodes. And this is actually not that surprising, because random graphs have particular properties. So that, for example, they usually have one big giant connected component, and there's also some isolated edges. So probably model can have a very good guess by just taking a look at the degrees of the nodes that we query, or also, for example, the number of triangles that they appear in. So to avoid this kind of spurious correlations, we defined a kind of purified task. So we have two n nodes, and these two n nodes are either two cycles of size n, and we query the two nodes that are not connected, or we have a big cycle of size 2n, and we query two nodes that are connected, but a diameter away. So for example, here n is 3, and on the left you can see when the case that the two nodes are not connected, and on the right you can see the case that the two nodes are connected. And actually, if you compare this with the random graphs, here it is not possible to have a guess by just looking at the, for example, degree of the nodes, because the degree of the nodes are the same. For example, the number of distance to neighbors are the same, and so on. So it's actually a harder task, and we remove those correlations. And we again represent the graph just using the edge set. And just to also make it a bit more formal, the difficulty, in the case that we have two n vertices and also two n edges, if we look at any n-1 edges, they won't give us any signal, because we can't really tell if they're coming from this two-cycle case or the one-cycle case. So we need to at least look at n edges to be able to say something about this problem. And we trained this task again with the GPT model, with GPT-2 model. And we see that the time complexity is exponential based on n. So as we increase the n, we need more iterations to learn the solution. And also, you're here using fresh samples. And this is bad news, because it's saying that as we increase the size of the problem, we cannot learn it eventually. Again, we want to kind of understand the reasoning behind that. And the reason is exactly the same thing, that we need to at least look at n edges to get some signal. And I'm going to formalize that notion in the next slide. So this is the new notion that we define, which is called locality. So we define locality as the minimum number of coordinates that one has to kind of attend to, or just consider, to get non-trivial correlation with the output. So we also define two versions for the locality. So one version is T-locality, which we will use for transformers, and the other version is M-locality, which we will use for MLPs. So the definition I gave you was for M-locality, and for the transformer locality, we also add the sum of the, for example, also here is a Boolean, so we give just the sum of the input coordinates as another component to this mutual information. So again, just locality is the minimum number of coordinates that we need to attend to just get some signal. And the transformer version of locality is just adding the sum of the bits, which gives us how many, for example, the ones we have and how many zeros we have, to the information of our problem. And it has some nice connections to other measures of learning that has been studied before. Also, we can very easily generalize the definition to other alphabets. The only thing that changes is that we cannot sum the input coordinates for the T locality anymore. Instead, we use the notion of P of x, which gives the empirical distribution of the tokens that are appearing in the input. So we can see that how many, for example, how many times each token is repeated in the input. For example, if it was a natural language task, it would be very similar to the bag of words approach that people use in NLP. Just to also for the cycle task, because the set of the nodes are the same for the two cycles and one big cycle, the T locality and MLP locality are the same. And they are both larger than n, because we need to at least consider n edges. So we have a conjecture here So we conjecture that, first of all, we put the conjecture for Boolean input and output functions. And our conjecture is that a function is learnable by MLPs if and only if it has a constant M locality, and similarly for transformers, if it has only a constant T locality. And so there are a few things in this conjecture which we should just make them more clear. So one of them is the exact type of architectures that we consider. So for MLPs, we consider MLPs with normal activation functions, with bounded derivative, polynomial size, and also symmetric and Gaussian initialization. And for the transformers, we particularly consider, again, polynomial size, bidirectional attention, and random positional embeddings. The other important factor is the distribution of the data. And we want to just avoid some edge cases that, for example, one input is appearing too often, and it's kind of just enough to memorize that output for that input. And we cannot easily generalize this theorem to MLPs and non-Boolean input-outputs, because that doesn't make much sense. But we can easily generalize it for transformers to polysize alphabets. So, for example, okay, I'll maybe explain it in the next slide. So we can prove this conjecture in some cases with some extra technical assumptions, which I'm going to skip. But I'm going to just explain it for the cycles task, because that's a running example. So for the proof to work, we need to add log n new edges. So these new edges are isolated edges that we add them to the problem for technical argument to work. And these new edges are isolated, so they don't change the label of the task that we had. And we can prove in that case that with the adjacency matrix representation of the input, and also large batch size, we cannot learn this task using either MLPs or transformers. And that's, I think, kind of a sad news, because we want to learn these tasks, and this is an important and fundamental task for reasoning. And the question is that what solutions we may have. And one of the most popular, I think, recent trends is the use of a scratchpad or a chain of thought reasoning. So in the scratchpad or a chain of thought reasoning, people also, instead of just giving the label of the final output to the model, they also give the steps that the model needs to take to reach at that final output. So basically breaking down, for example, if it's a mathematical question, instead of just giving the final answer as a number, people also give the complete solution to the model and expect the model to also generate the complete solution. Just to have it a bit more formalized, we have the input x1 to xn, and we want to generate the scratchpad and finally the output autoregressively. So we first generate y1, then y2, and so on until ym, which is our final label. And this y1 to ym is our scratchpad. And the thing that happens is that we can break one maybe hard learning task into smaller steps, such that each step is quite easy. So for example, maybe this Matterhorn picture would explain it better than me. So it's, we have the input, and we can maybe come up with some simple target y1, which is the first intermediate target, then y2, that is easy to learn from y1 and x1 to xn, and then y3, and so on. We can climb this path to get to the final label. So we can, of course, extend the previous definition that we had of locality to this autoregressive setting. So in order for the autoregressive model to be able to learn the function, we of course need the constant locality, but this time for each of the intermediate targets. So for example, we need y1 to have constant locality based on the input, and then y2 to have a constant locality based on the input and y1. So in a sense, we can just break the high locality of the target into constant localities using the scratchpad idea. So we just need each of the scratchpad tokens to be of constant locality to be able to learn the task. Here is just one parity function example, which maybe can explain this nicely. So the parity function is that we have n bits, and we want to compute each of these n bits are -1 or +1, and we want to learn the product of k of them. And this is one of the canonical tasks in study of theory of machine learning, because it's a hard task that as you increase k, the task becomes harder. And you can also see it here because the locality is also k, because we need to attend to at least k bits to get some information. And we can break it with the scratchpad quite easily. So in the scratchpad, we can just compute x1, then x1 times x2, then x1, x2, x3, and so on to get, and finally the final target. And at each time step, each part of the scratchpad is only computed based on another previously generated token in the scratchpad and one token in the input. So basically now the new locality is 2. And that's the reason that we can climb this, again, the path and learn this parity function more efficiently using the scratchpad. So getting back to our running example for the 2 cycles task, one solution that works is just sorting the edges from the source query node. So here, for example, we want to see that whether A is connected to M or not. And we can start from A and go to the next node and so on. And if we reach at A again, it means that we are not, the 2 nodes are not connected. And if we reach at the target or destination node, we can see that the 2 nodes are connected. So we just need to kind of perform a BFS or DFS algorithm in this case. And actually, we can just see this in experiments, that if we use this format of scratchpad training, we can break the exponential time complexity of the problem and learn it quite easily for different sizes. And also note that we can design scratchpads of different locality itself. So for example, we can have scratchpads of jump 1, which was the same version that you saw, that A goes to B and then C and so on. Or we can, for example, skip one node in between, so A goes to C, then E, and then G. Or we can have other jumps. And the higher the jump, it would increase the locality of the task. And as expected, it would make the task harder to learn. So there are 2 points that are important. The first one is that when we add the scratchpad to the task, we are changing the game, because it's not the same as learning without just labels. Because now we have more information, we know that how the task is done, and we are giving that information to the model. So we are changing the game, and we conjecture, and in the similar kind of spirit of the previous theorems, prove that unsupervised forms of scratchpad cannot really help with the learning and cannot break the locality barrier. So we really need more information, and we need to supervise the scratchpad. So giving the scratchpad only as a kind of computational memory or power, it's not enough. And the other problem is that we may again have this problem with the scratchpads, and that when we change the distribution, the scratchpad may not generalize. And this is something that we can address, and we will in the next slides. So just we do an auto-distribution experiment. So during training, we have 4 cycles of size 3 or 2 cycles of size 6. So we make the training set such that we only need 3 reasoning steps to get a label. And for the test set, we make this normal cycle task with 12 nodes. So we need at least 6 reasoning steps to get the output. So it's just the size of the graph is the same, the number of nodes is the same. It's just the number of reasoning steps that differ. And as you can expect, because with the full scratchpad overfits on on the number of reasoning steps, we cannot generalize to the out-of-distribution. And to address that, we focus on the repetitive structure in the scratchpad. So if you notice that the same operation that is used to compute x from A is used to compute c from x and also m from c. And we can use this repetitive structure. So there is the same function that gives the same, the next node for all of these functions. So I'm just gonna, how much time do I? 1 minute. Okay, give me 2. But we can put forward the general format of a scratchpad, inductive scratchpad. So we have the input, and state 0 is just computed based on input, and after that, each state is just computed based on the question and the previous state. And I don't get into the details, but we can introduce 2 new tokens, this memory token and this hash or number string token, to enforce the inductive structure of the scratchpad, such that when we give the model the question and all of the states, it just reasons based on the last state and the question to get the next state. So it's just in general, in the full scratchpad, we need to attend to all of the scratchpad to get to generate the next token. But here we make this attention simpler and by enforcing this inductive structure. And as expected, we can easily change the normal scratchpad format into inductive and also generalize instantly to out of distribution for the previous example. So I will skip this one and okay. This is a summary of our theoretical results, and I think there was a hype that models can, maybe transformers can generalize and learn any kind of function computable by a Turing machine, but we conjecture and also prove in some cases that it's not possible without having supervised scratchpad. Thank you.
Okay, so maybe one quick question if there is, and Anya, you can already join. All right, so this is the last presentation.
Okay.
All right, so Anya.
Yeah, hello everyone. I know my presentation is the last one standing between you and lunch, so I'll try to keep it brief. And I'm also not presenting any research results. I'm announcing an initiative starting at EPFL. So, as I'm sure you have all experienced, state-of-the-art AI models can be pretty impressive, for example, with mastery of language. However, they lack reasoning capabilities, especially for problems that require deep understanding and long reasoning chains. While we have some notable exceptions for specific domains, such as alpha geometry, that we heard about today, we don't yet have a general AI system that could robustly solve problems across various math domains. So what is missing and how could we bridge this gap? Historically, one of the primary drivers behind getting more capable AI models has been the increase of the size of their training data set. However, unlike general data, where it is relatively easily to label it and generate it, mathematical data is scarce, and its creation and curation requires a higher level of expertise. To address these challenges, we're starting the AI for Math initiative, and the aim of this initiative is to establish a network between academia and industry, where we would encourage open collaborations between researchers, students, and engineers proficient in maths, formal verification, and AI. To give you a better idea of what kind of directions we're planning to pursue, I'll now quickly list a couple of them. First direction is about educated data augmentation. Here, the goal is to create new problems from seed problems that we can collect in math. By doing this, we would expand the size and the scope of data sets. And this also requires non-trivial evaluation methods to judge the novelty of problems and classify them on top of the generative process. Second direction is about providing feedback to AI-generated responses. So just as reinforcement learning from human feedback has been crucial for developing top-tier chatbots, it's likely that to build top-tier reasoning models will also need some human feedback. At least before we can get to models that can independently discover new knowledge, we need to bring them to the level of mathematicians. And for that, we will need mathematicians to interact with models, guide them in reaching solutions, and point out their mistakes. Next, we're also interested in formal mathematics. We've heard today about the immense potential of formal mathematics and the opportunities it opens up. One direction that we would like to pursue is to build a corpus of translations between informal and formal mathematics. Such a corpus would help us train AI models for formalization and automated theorem proving, and having such models would help mathematicians more easily leverage formal mathematics for their research. One direction that we were considering for getting such a corpus would be to informalize MathLib, which is a library of formal mathematics in LIM4. Finally, we're not yet decided on all the directions we want to pursue, and we're still exploring and open to other suggestions and ideas. Here's the list of current members of our initiative, and we're looking for other enthusiastic people to join our efforts. So if today's event inspired you, and if you're passionate about the future of AI in mathematics, we would like to invite you to join our initiative. And to do that, you can fill out our survey. You can access it by directly scanning the QR code, and there's also the link on the website. Thank you.
So, okay, we are done for today. Thank you very much for all the great talks from all our speakers, the ones traveling from far and the local ones. We covered a pretty broad spectrum in this area. Hope to see you again at the next event. Bon appétit. Est-ce que je peux m'incruster au déjeuner? Alors, le problème, c'est que j'allais dire oui, j'avais même pensé à t'inclure, mais j'ai genre 5 personnes qui m'ont posé la même question. Et maintenant, je ne sais juste pas à quoi ça va ressembler quand on débarque au resto avec 5 personnes de plus. Donc, si ça ne t'embête pas de devoir te retrouver la queue entre les jambes parce que le resto nous dit on ne peut pas, tu peux, mais.
On peut pas leur passer un coup, c'est quel resto?
C'est un peu loin, c'est à 20 minutes de marche.
On peut pas leur passer un coup de fil et leur demander.
En fait, j'ai déjà demandé ce matin qu'ils étendent de 5. J'ai trouvé 5 clubs, il y en a encore 5 autres. Je sais pas si.
Non, mais alors dans ce cas,
mais je pense que tu viens, et puis au pire, je dis juste pour être prêt au fait que si vraiment nous disent désolé, on n'arrive pas.
Mais ouais, mais c'est où? Parce que c'est le resto un peu cool près du lac là-bas, en bas.
Ouais, exactement. Ouais.
C'est super ça.
Viens, et puis au pire des cas, voilà. Mais je pense que si vraiment ils disent désolé, on n'a pas la place, soit prêt à ça. Ou appelle-les si tu veux.
Mais ouais, c'est quoi alors?
Merci beaucoup alors.
Je vais envoyer le mail. Je sais pas te dire.
Essaie de les appeler ou viens avec nous.
It went very well, congrats.
It went well.
Yeah.
Right, and the crowd was there.
Yeah, exactly.
But I think, and
Exactly. Yeah, hopefully.